Hello and welcome to the first lesson in electricity. We're going to look today at the basics of electricity, what you know from year 7, and then we're going to build it up in later lessons into the more complicated GCSE topics. So let's have a look. What do we need for an electrical circuit to work? Clearly this circuit here is not working, and it should be obvious that that's because there is not a complete circuit. There's a gap here, which means the electricity will not flow round and the bulb will not light. What about this circuit? Well, obviously there is no battery. There's a massive gap here, so it's not a complete circuit and there's no battery, so the bulb isn't going to light. If we have a complete circuit with a battery in, then the electricity will flow round and it will have a circuit that's working. Some really basic ideas that you learnt in year 8. So what else does this show us? Well, even if we connected this circuit up with a wire, it's still not going to work because there's no battery. So we know that batteries store energy. They are a chemical store of energy, and they transfer that energy electrically to things that are in the circuit, such as a bulb. So electricity is a transfer of energy. Here is a quick summary of the basic ideas from year 8 for you to make a note. So now we're going to look at a little bit more detail about what's going on inside the wires. Now you'll know from your chemistry lessons that if we look at a metal, the structure of metal is a bit like this. There's a positively charged metal ion surrounded by a sea of delocalized electrons. And in a metal, there are millions and millions and millions of these, so many delocalized electrons. And what happens when you connect a wire or a metal wire up to a battery? Let's have a look. We're going to close the circuit and you can see what is happening. So we've got our piece of metal here. We've got our atoms, the black circles, and we've got our electrons, the blue circles. When the wire is, or when the switch is open, the electrons stay pretty much where they are. When the switch is closed, the electrons all start to flow round. So when we make a complete circuit with a battery, the electrons are pushed from one end to the other. This is electricity. It's actually current, but we'll talk about exactly what we mean by current in a second. We can think of it as just electricity. Electrons all moving in one direction. So here is a quick summary of 2 key ideas. Firstly, that metals are good conductors because they have many delocalized electrons. Insulators such as plastic or glass do not have many delocalized electrons. When a battery is connected to in a complete circuit, it exerts a force on the electrons and makes them move. Okay, we can see that here. Why would the electrons move? Well, they move because there's a force on them. Where does that force come from? Well, it effectively comes from the battery. If you study A-level, this would be called electromotive force, but we just simplify it. We call it potential difference. And on this slide here, it tells you what the formula for potential difference is. Potential difference is work done per charge. So what do I mean by that? When I close the circuit here, the battery transfers some energy. It does some work. Work done means energy transferred. That energy is transferred to the electrons and they move along. So each electron gains some energy, and the amount of energy it gains is known as the potential difference. So if you go and find yourself a battery or look on the back of your phone battery, you'll see a number in volts. It might be a 9-volt battery, it might be a 1.5-volt battery. What that means, the number of volts is the amount of joules that each electron gets effectively. So a 9-volt battery is transferring more energy to each charge than a 1.5-volt battery. So your laptop is going to have a much higher voltage rating than something in your remote control for your TV, for example, because it needs more energy to work. So which direction do the electrons flow? Well, you need to know two things that are basically the opposite, and this is a little bit confusing and odd. A man called Benjamin Franklin did some work on electricity a long time ago, and he decided that current was going to go positive to negative. Just decided that. And then later on, some other scientists discovered that he was actually wrong, and it was electrons moving from negative to positive that is current. So they had a decision then. They could say, right, we could rewrite the textbooks, we could correct the mistake that was made, or we could just leave it. It'll be cheaper and easier to just leave it and not change all the textbooks. And that's what they did. So now there's two things that you need to remember. You need to remember that conventional current, so current as we normally talk about it, positive to negative. But electrons actually go negative to positive. You just have to remember there's two separate things. Here is the information summarized for you to make a note. So let's go back to this slide here. We're now going to talk about the second important thing with electricity, and that is current. So we've said that potential difference is the work done per charge, the energy per charge. We are now going to look at current. What is current? Well, current means flow, or it means movement. Think about current in a river. And it's pretty much the same for electricity. Current is the rate of flow of electrons, how many electrons are moving per second. So here we could count up the electrons if we wanted to, and we could get a current. If we had a battery that had more energy, of a higher voltage rating, the current would be higher because it's pushing the electrons around a bit more. So I'm going to take this opportunity to switch to a simulation of electricity. So here, and I will link to this in the classroom so you can play with it yourself. Here we have a circuit. It's a complete circuit and there is a battery in it, so the electrons are moving round. What happens if we click on the battery and we increase its voltage rating? What's going to happen to the circuit? Well, two things are happening. Firstly, the bulb is brighter. It's brighter because we're increasing the voltage, so we're increasing the energy per charge, and therefore we're increasing the amount of energy that can be transferred to the light bulb. Secondly, you will notice the electrons are moving more. Right? We are increasing the amount of them that are flowing past a point in the circuit. We're increasing the current. So a higher voltage is going to create a higher current because there is more energy and more push in the circuit. Let's do one more thing. Let's just see what happens if we change the resistance of the bulb. You can probably predict what's going to happen to the circuit, both the brightness and the current. All right, you can see that the current has decreased. Now we're going to come back to resistance next lesson, so we're not going to talk about too much about this now. But you can play around with it yourself and you can see what's happening, and the next lesson will explain this properly. Let's go back to the PowerPoint. So let's summarize that information. Okay, electrons cause current in metals. However, actually in physics, we say charges rather than electrons. Current is defined as the rate of flow of charge. Rate means divide by time, or how quickly. So rate of flow of charge just means how many charges move past a point in 1 second. And there's a very important formula here. You actually don't need to remember this formula if you remember this definition here, rate of flow of charge, because then we know that rate of flow of charge means charge divided by time. But this equation or this definition is something you must remember. So I will link to the simulation in your classroom, and I encourage you all to play around with it and see what happens when you change the voltage, when you change the potential difference, the current, the resistance, etc. So let's look at a couple of different questions now. A current of 3 amps flows in a circuit. How much charge passes through a point in 30 seconds? Classic exam question. So firstly, what we're going to do, we're going to list the quantities that we know. We know that it says the current is 3 amps because it tells us here. We know that the time is 30 seconds, and it tells us to work out the charge. So now we need to think what formula relates these. Well, current is the rate of flow of charge. Current is charge divided by time. How can we work out the charge? Let's put in our numbers. 3 amps is our charge over our time. So now we need to solve this equation. And I know that you will know how to do this for maths. It should be fairly easy to figure out that charge is 90 coulombs. These questions are super easy if you write it out like this. If you write out everything you know, what you're trying to work out, if you write out the formula, if you put in the numbers, and then you can work it out. You're always allowed to use a calculator in science if you're not sure of the maths, but most of the time you can probably do it in your head anyway. All right, the second type of question you're going to get is about potential difference. So it says a cell transfers 7.5 joules of energy to 5 coulombs of charge. Calculate the potential difference of the cell. So again, what do I know? I know what the work done is, 7.5 joules. I know what the charge is, 5 coulombs. I know what the potential difference is. Sorry, I'm trying to work out the potential difference. So what equation links these 3 things? Well, it's our definition of potential difference. Potential difference is the work done per charge. So now we're going to fill in the numbers that we know. So we're trying to work out the potential difference. So it's 7.5 over 5. Putting it into our calculator, doing it in our head, tells us that potential difference is 1.5 volts. These 2 types of questions are the ones you're going to get most in the work for this lesson, and you're also going to get some basic questions about definitions of current, definitions of potential difference. So in summary today, we've talked about what electricity is. It's a transfer of energy. We've talked about why electricity flows. It will flow if there's a complete circuit with a push, so a push that comes from a battery or a power supply. We've talked about what potential difference is the energy per charge, the energy per electron. What current is, it's the rate of flow of charge, how much charge flows in 1 second. And we've given a couple of examples of how to do calculations. So your work is going to involve all of these things. And there will also be all the information summarized for you as well in a document, so you can read it as well if you are unsure of anything.